Astronomical. So now we're being recorded. I'm Gary. I'm the president of the club, so welcome you all here. I just want to tell you a little bit about the club. It's a club of amateur astronomers that's down here in the South Bay. We've been around for 75 years-ish. And we are the ones who operate the Foothill Observatory at Foothill College. So that is open every Friday evening and Saturday morning for free observing of the night sky and the sun on Saturdays. We're currently closed due to mechanical issues with the telescope, but we're working to resolve that. We hope to be open. I don't think we'll be open this weekend, but we hope to be open for the following weekend. And we do have an event that we're planning in the middle of September, which is to participate in NASA's Observe the Moon Night. So we hope to have a big public event at Foothill College in honor of that. That's Saturday the 14th, I think. Again, we're a club. Benefits of the club include, if you're a member, you get free access to our large pool of loaner telescopes. So if you ever want to figure out, how to use a telescope, we have simple ones up to some much more nicer ones, like Schmidt-Cass 8-inch telescopes, computer control. So if you want to learn how to use a scope, this is a way to do it. And then finally, we also have our own private observatory location up in the Santa Cruz Mountains for the serious types who want to take pictures of the night sky, using your own equipment or, again, our equipment that we have up on the site. So that's enough about the club. I'm now going to pass it over to our wonderful speaker chair, Antonio, who does such a wonderful job finding these wonderful speakers. Yes, you can do it.
Hey guys, welcome. Thanks for coming in. I'm just curious, kind of show of hands, who has seen the movie The Martian? Yeah, okay.
What's the question?
Who has seen the movie The Martian with Matt Damon a few years ago? You have to. Okay. So, yeah. You've seen it, okay. So remember when he's out there, he's got a bunch of problems and he's got to figure them out? I think this is exactly what you don't want to happen. So in order to avoid these types of situations, or even the movie Apollo 13, when Houston, we have a problem. If some of you watched that one too. When you're out there, Houston can say, well, we feel for you, but so in order to avoid these kinds of issues, Dr. Vera has done an incredible amount of work. He's worked at NASA Ames for over 25 years in a number of different projects, but his most recent stuff is precisely that. What do you do when the astronauts are way beyond the orbit of the moon? And you want to make sure that there's enough backup, redundancy, whatever it is, that they can figure it out. Come back safe. So with that, thank you so much for speaking to the club.
Thank you for inviting me. Can everybody hear me okay? Okay, so yeah, let me say just a little background too. I have been there 25 years. I spent my first 3-4 years, that's a little longer, maybe 7 years, working particularly Mars missions, Mars rover missions. So the first mission that I ever really worked on was the Mars Exploration Rovers mission in 2003, right, the 2 rovers. Then we worked the Phoenix Mars lander, which was a polar lander, not a rover, and then the 2013 Mars Science Laboratory, and then Mars 2020, although I haven't really been involved in that. Around 2006, 2007, we started working on what was then the Constellation program, which was sort of the planned replacement for shuttle, and which is sort of where we are now, many years later, right? With more kind of commercial provision of access to the space station, right? So the decision was made. There was something called the Augustine Commission report, and what they found is, look, low Earth orbit is now easily accessible. It's not exploration anymore. There's nothing particularly hard about it. So commercialize. Give that to, and right now, Boeing not so well, but SpaceX and Blue Origin, to have them bring things up and people up, crew up to the space station. and then have NASA focus on deep space exploration, back to the moon and onto Mars, which is where we are. So around 2018, getting to be close to 6 years now, I was asked to work on what are the risks associated, basically in a sense, with like human-computer interaction, human systems integration, for in general for upcoming human spaceflight missions. And it was at that point that really started thinking about it. I thought, no, really, I'll kind of talk about this in a little more detail. We haven't really had problems. Certainly, we have had no loss of crew, loss of vehicle issues for the last 20 years, 24 years. But it is in part because we control the vehicles from the ground. And so you started thinking, well, as we go and beyond where you start getting communication delays, this is going to get harder and harder. So that's what this presentation is about. And again, thank you very much for inviting me. And I'll try and tell it a bit like a story. So let me start with a couple of just kind of background stories. So there's a point at which we kind of began thinking about, is there anything, are there lessons from other terrestrial applications, ways that we have done it on Earth, or things that we've done on Earth that are similar? And in some ways, a similar kind of expedition or expeditions were the 2011, 2012 South Pole expeditions, right? So, a lot of us have heard about these. So one was Norwegian mission, Amundsen's team. They made it. They succeeded in getting to the South Pole. And then Robert Falcon Scott's team, British team, they all perished on the attempt. And in particular, what's interesting here is it was a long trip, right? So 5 months, not long compared to Mars. But so the there and back trip was 5 months. So you had small teams, about 5 on each team, no resupply. Once you were out there, you were out there. And they'd staged some things in advance, but not too far, right? Once they were really on their way to the pole, that was that. No possibility of rescue back then. And then no outside communications. So whatever you had with you, whatever, that was it. A bunch of factors went into the outcome, right? And, in some ways it's really anecdotal, right? But among the things that happened, right? So the Robert Falcon Scott team, a big focus on technology and on equipment. The Norwegians were really they were out there in the field trying, like they spent, weeks out there, just with the equipment they had. There were a couple of really big decisions that the British team made that affected them. So one was they chose to bring horses because they could pull more weight. And turns out, and they, again, not a lot of field experience there. Horses turned out not to be very good in deep snow and the cold at all, right? The Norwegians showed up with dogs like, generally people do. There was another big one, right? So one of the big technology things was they developed, and you see it in the picture here. They developed it was a transporting pad, like a tank, right? So with these tracks, and then so it was the equivalent of horses too, right? They had 3 of those built, and they had the engineer who designed and built them coming with them. And about a week or 2 before the mission started, one of the investors, another British explorer, a wealthy British explorer, said, I want to come on the mission. So they bumped the engineer. All those stopped working pretty quickly. And so that, plus the horses dying, and then, so it was, the takeaway from these is that this long mission, small group of people with nothing but what they have with them, and no help from the outside, no resupply, no rescue, is very risky, and we hardly ever do it. So let me give you another example. So 1492, the first Columbus trip to the New World, risky. They didn't really know where they were going, right? But this is interesting. So also 5 to 6 weeks. No resupply along the way, right? If there was, it was going to be by good luck of finding some, island or somewhere to stop in general. Sometimes they would Once they had gone more than once, they knew a couple of places to stop along the way. Again, no rescue, no communications, large teams. So about 30 sailors per ship. They had vehicle redundancy, right? So they had 3 ships, and if one problem happened with one, they could bring the sailors onto the other ones. They had carpenters, sailmakers, pilots, multiples of each, and they had all the equipment to make new sails, to make new masts. And this is kind of a bit on the opposite side. Like when we can, this is how we run things, right? You take all the experts you need, you have redundancy of vehicles, you have, both, the workforce and the expertise. So the way we think about it is dangerous, extreme environments or safety critical operations. Those are the 2 things, right? So Mars, and let me just throw a couple of just facts out there and I'll sprinkle them, right? So it'll take about 9 months to get to Mars, okay? Unless we really change our propulsion technologies. But right now, anything that's in space is going about 17,000 miles an hour because that's breakaway speed, right? So once you're in space, and then, we don't tend to have, getting to go faster in space is hard right now, right? So it would take about 9 months to Mars. We launch right as Earth comes up on Mars. And then, Earth is already a bit past Mars by the time, the crew is just a month away, right? So once the vehicle is 4 weeks away from Earth, you can't turn back and go back to Earth. You have to basically head back the other way and literally come around to meet Earth as Earth comes around the other way, and that's a year, okay? So again, no evacuation, no way out, no resupply on the way either. You can't stage things between Earth and Mars. These are all moving things out there, right? So orbital dynamics are complicated. That the idea of having, and on top of it, you probably have to stop, right, on your way to Mars. And again, the whole big thing is the energy required to either stop and dock or whatever. So something would be having to move in the same direction, right, at the same speed for you to dock with it. So something would, you'd have to. So there aren't plans right now for resupply either. Just like in the movie The Martian, there are, the current plans all have us, putting supplies on the surface 2 years before. There's a launch window every 2 years, right? As Earth comes up on Mars every 2 years, roughly. And so, 2 years before, maybe 4 years before, we start sending things to Mars. You put some in orbit, you land some, you land the return vehicle, you land the food, hopefully make sure everything's okay. Now, again, back to how do we do this, right? So this basically represents, you see here, one-way communication delay, mission duration, and hours, how long does the mission last, and then evacuation, delay, and resupply. So it's a bit of a, but, just again, think about it as you go up this way, you're moving away from health in communication and in the ability to get out of trouble, and this is how long is your mission. So a lot of stuff that we do, airplanes, here you see Apollo, the shuttle, is a large-scale ground-based anomaly resolution and repair team, right? So it's really mostly done on the ground. Minimal onboard corrective maintenance. If things broke, you were like, okay, don't touch anything. On Apollo 11, and this is, if you go and, all this is public, everything I'm going to present is actually publicly available data. On Apollo 11, they had a circuit board issue, and Armstrong, repaired it with a pen, right? Because they had no tools. Why did they have no tools? Because the idea is, worse you turn around, like Apollo 12, right? Sorry, Apollo 13, right? Apollo 12 Apollo 12 got hit by lightning on the way up, right? So every mission had some doozies, it turned out, except Apollo 17. Highly trained ground-based technicians, specialized skills, and the crew has general skills, okay? That's how it is, so pilots, highly skilled, at what they do. And then on the ground, you have all this other expertise, right? I mean, on the ground, you have all the kind of separation of the direction, who's going where, and if there's an emergency, clear that, like everybody out of the airspace so we can land, right? aircraft carriers. This is Antarctica, right? So McMurdo Research Station. Submarines, nuclear submarines. These could go down for months, but they have about 150 sailors. About 75 of them are actually working on keeping the vehicle alive, right? So, and shifts of 24 hours. We interviewed a bunch of them, right? So you have the sailors working the hydraulics, the electronics, the nuclear side, the IT, all the different elements, and they're working in 3 shifts, 24 hours a day to keep the submarine alive, right? Their goal, of course, is not to come up, right? You kind of break the mission if you have to come up. McMurdo Research Station in Antarctica during the winter, they get down to about 250 people. They often have a doctor. Once in a while, they've had a situation where somebody's had to do remote guidance. Somebody in Australia has done remote guidance of a surgery at McMurdo in the middle of winter because you can't evacuate somebody, you can't get there. And but we can communicate, at least to some extent in this one, sometimes not well. Aircraft carriers, 5,000 sailors. I mean, a lot of them are doing missions, but again, long duration, they're out there, right? And so if you're going to be out from help, you bring a lot of humans, right? And those humans are very good at problem solving. They're and especially you get expertise and you just get a lot of work power. And then every now and then you have these more difficult ones, like the space station, right? So then you have a small, highly trained onboard crew for troubleshooting and repair. Expertise and resupply from the ground. Like, for example, we talked to some, people who work on oil rigs in the North Sea, which was interesting. A couple of Scottish people, we spent the first half hour trying to understand what they were saying. But, really, like, they're saying in a big storm when things go wrong and you can't helicopter people in, yeah, it's hard, right? Especially if, like they, but generally they, people bring in resupply, you need a piece of equipment, et cetera. And then you have, getting out to repair things like what we call an EVA, extra vehicular activity, either floating around the space station or in the case of, say, oil rigs going down. Those are hard, those are difficult. You plan those very carefully. Those are not willy-nilly activities, right? So this is kind of how we do things. It's either a really big team if we can. If it can't be a really big team, it's really short. You're in, you're out, like Everest. Right, Everest is another good example. So it's short, and rescue can be hard, and the mortality rate for Everest is still 1 in 100. So it's higher than certainly than NASA will accept for our mission. So so let me give you a picture here. This is Mercury, Gemini, Apollo, Skylab, Mir, Shuttle, ISS, Gateway, which is our next little space station that is going to go around the moon. Artemis 3, which is the first lunar landing mission, right? So Artemis 2, which is supposed to launch next year, will go around the moon with crew. Artemis 3 lands, then a lunar base camp, and then Mars, right? So this is the progression of it. This is what we've done up to now. All of these missions are either short duration and one-time use. So Apollo, the longest mission was 13 days, right? So relatively short. The vehicle came down, we caught it in the water, and that was that. We didn't reuse that vehicle, which is actually, there's a reason too. There's an interesting thing to, like, any guesses why we never reuse the capsules?
Why the SpaceX?
Yeah, no, it's funny, you send them like a fireball, and you shake them and everything. No, it's the salt water, right? That once you put them in salty water, it's very bad. So the Russians, for example, reuse the Soyuz because they land them on land, which is rough and dangerous. But so either short duration, one-time use, or short duration maintained on the ground, shuttle. Longest shuttle mission was 17 days, or long duration and easy access from Earth, which is space station, right? So space station, it's, on a rocket, it's 8 minutes to low Earth orbit. Then you spin around until you come up and meet with it, right? But so we are constantly resupplying the space stations, right? So the space station has had quite a serious atmospheric leak for almost 3 years. And people are working it all the time trying to figure out what it is, but we're not like that anxious because, you know, every couple of months we send up more air, right? On your way to Mars, all these things become far more urgent, right? You can't be losing air, you can't be losing water, you can't be losing power, right? So this is our experience for the last 60 plus years of human spaceflight. This is it. We don't know at this point how to do, now longer stays on the moon are going to be harder. Not as hard, and Mars is a whole different ballgame, and I'll tell you why. So, like I said, you know, Mars, as you start moving away from Earth, will spend about 70% of the whole mission with communication delays greater than 15 minutes one way. So at its maximum, it'll be 20 minutes. It could be even longer. There are at least some orbits that some return flights that put Earth going away first and kind of slingshotting back in. That would actually give you more like a 25 to 30 minute one way for a period of time. So, but we're talking ballpark, you know, 40 minutes, so half an hour to 40 minutes to, you know, an hour. And so two-way comm delay. So if something happens on board, and, you know, part of what we tried to understand is what kind of something, how do you handle that, right? Because right now you handle it by a whole bunch of people on the ground knowing about it right away. So we've done a bunch of background research, and I'm just going to show you some of it, but some of it is sort of interesting, right? There's been not a lot, actually, let me take that back. There's not been a lot of research on communication delay. Not surprisingly, it's not a big thing for anybody other than NASA, right? So, you know, what are the effects? What are the impacts? How do we look at communication delay? So, of all, you know, here, this is an analysis that we did, you know, 2 years ago of the research on communication delay. And so, you know, here's the amount of communication delay: 0 to 4 seconds, 10 seconds, 100 seconds, 600, you know, 1200. This is about an hour, right? So what we're looking at for Mars. This is about what we're looking at for Mars. This is about what we're looking at for the moon. Moon, by the way, is going to be much longer than it was during Apollo, which sounds crazy, but the Deep Space Network has actually, because as we built it out, the Deep Space Network was all about communicating with things that were on their way to Venus or Mercury or, right, Jupiter, and so seconds didn't matter. And so we built it out with enough kind of weak links in the chain that it looks like for command data will probably go faster, but video and audio data will probably be 7 seconds one way, so 15 seconds. Doesn't seem like a lot, but it'll definitely impact the ability of the ground to supervise the work that's being done. Because right now, when the crew are doing anything hard, the ground is watching them in real time over their shoulder, right? You can watch it on TV, right? They have cameras and they're talking to them and say, oh, don't forget to close that. Okay, yeah, put that back. Or no, not that one, the one next to it, right? So that's here. This empty box represents a gap in research on 10 seconds. We've had a lot of research at 1 minute, 5 minutes. I don't know why, where's 5 minutes? And then, but also another big gap here for Mars. We've done work, and these are all like, this is DRATs, it's desert rats. It's bring a whole bunch of robots and crew and everything to the desert for a few days. That happens frequently. NEMO is the NASA Extreme Environments Mission Operations. That's an underwater lab off of the Florida Keys. So these are all environments where we go test stuff like this, right? The other big question is, what did we look at? Because when we look at communication research, and communication delays, a lot of it, what do you know, what kind of situation, if somebody's just sitting there making dinner, communication delay is not going to make that much of a difference, right? Like if somebody, so normal operations or EDA, which, you know, it's a complex procedure, or medical emergency, or maintenance, or contingency where there's something that's off, and then troubleshooting, trying to fix a problem, right? And you see from Mars that maintenance, contingency, troubleshooting is a big gap. And this turns out to be the hardest thing. And often when we have looked at this in some of these experiments, we look at how well did the team perform? Or, what was the crew training for it? We don't look at, did they fix it? What was the outcome? Like, we don't treat it like a hard problem. And so in some of these, you may have seen, have you seen that in the last, I think 3 years, NASA built a printed habitat? It was in the news, right? These 3D printed, it's like a 3D printed home, but they built a Mars habitat over at Johnson Space Center in one of their big high bays. And then you put people in there for months to pretend that, they're in a Mars environment. When early on, I had the opportunity to talk to the principal investigator, and she asked, okay, what would you want us to do to research? And I said, well, I think we'd want to basically have them with communication delay, which they were planning to include, to have something break that's, difficult to fix, and that they might fix it now without some support from anybody. I'm like, what kind of stuff do you have in there? And they're like, we have a fan and a toaster, right? So we have these environments that we create to simulate, and then we put nothing. I mean, basically, when you're on your way to Mars, in all these environments, when you're in the submarine, you are in a machine that's keeping you alive, right? And we don't treat it that way, right? We create these environments where we're not able to really test that, right? The fact that the machine is keeping you alive, and the humans in it are keeping the machine alive, often 24 hours a day, right? So what gets hard? So here's, this is notional. This is some kind of rough assumptions for this, right? So this gray area here is what the ground does, and this blue area here is what's being done up in space, right? With even a second of con delay, you can't control things directly anymore. So if you're trying to control a robot in space that's going to grab a vehicle, and you've got a second or so, or let's say you want to do telesurgery, even a second makes it almost impossible, right? You can't have that kind of delay if you're doing direct control. So more than a second or so, which is what we have for space station, and you start, like the crew on board a space station has to do that work. Anything that's direct manipulation of a robot or anything like that, it's all, like the robot arm, the crew does it, right? Is that, no, we would much prefer for the ground to do it, right? But we can't, right? Because again, you're holding an astronaut out there, you're capturing an incoming vehicle. Somewhere at about, and we don't know because the research wasn't there. That was what I showed you before. Somewhere probably at around 10 seconds, 5 seconds, 15 seconds, you're going to lose the ability of a group of experts to oversee and guide the procedures that are being executed by people who don't have quite the expertise, right? So somebody's doing a hard procedure, and they're the next step, and all of a sudden your group of experts is seeing stuff too late. The next thing that's going to happen, and when you talk to crew members, you talk to astronauts, and they say, one of the things that we really depend on the ground on is big irreversible decisions. That's what they call it. They call it big irreversible decisions, right? So it could be anything. It's like, okay, I'm going to drill a hole in this thing, and once I drill a hole in it, that's it. It's not going to get undrilled. How long is the crew willing to wait for the ground to say, yeah, go ahead and do it? Because again, the crew will tell you that's really important. 2 minutes, 3 minutes, right? So you're willing to wait more, right? I mean, that's like but we don't know, it's a bit of a gap, but somewhere in there, you're not going to be, especially if you have a long procedure with a lot of big irreversible decisions, you're not going to be able to wait for the ground to give you that. And finally, problem solving. And this is the biggie, right? At some point, problem solving, you can't wait for the ground to problem solve for you. Troubleshooting the system, right? So that has to move on board. So once you're basically, right here, crew has to kind of directly pilot the vehicle, manual, et cetera, like Armstrong hand landing, the lamb on the moon, right? That happened, Apollo 11, right? So with the moon with 1.5 seconds one-way convoy. At some point, then, crew has to execute complex tasks without real-time support. Then the crew must make real-time critical decisions independently. And then finally, autonomously manage vehicles, stay, fix problems as they happen, or at least safe the system. Like I said, there's not a lot of like good just empirical data on this, but we know that once you get to say 40 minutes until you get support from the ground, and it'll be longer too because the ground has to think about it too, right? This will be a surprise for the ground. And so, so what we did in order to make this a more tractable problem is we said, okay, what is it that the ground does now that depends on real time? What is that slice of activity that the ground does that if you didn't have real time breaks? Because there's a whole bunch of stuff that mission control is doing all the time that isn't that urgent. Like I said, like right now we have atmospheric leaks, but we know we can send up more air, so we work it slowly. Meetings every day, and people come up with ideas, et cetera, right? So let's assume that the ground is still going to continue to do as much as they can, maybe more. It's probably going to be a harder thing for our friends in Houston. So, but the next thing we kind of got to was like, how hard a problem is it? How often do bad things happen that we have to worry about? Maybe it's pretty infrequent, right? Because it turns out, for example, we worry a lot about medical events, medical emergencies. At some point I started like, how often do medical emergencies happen? We never really had one on space station. 24 years of space station, right? We've had a couple like, bad days, right? And, headache. Definitely everybody has a backache. People generally don't feel well because they're in space. But, beyond that, right? Like, and so I was like, how many doctors are on a submarine? Turns out 0, right? You have a paramedic type person with some training on a submarine. And when we talk to the submarine sailors, they, we're like, how often does stuff happen? I'm like, no. One person had done 4 years, and they said, never. I mean, there was another interesting lesson there, which was, what if something bad does happen? And they said, well, we probably wouldn't go up anyway. So that was interesting too. But that's the difference between NASA and the military. Okay. So at some point we started digging into, again, how often do bad things happen? Okay. There's a range of bad. So I don't want you to walk away from this saying, oh my God, although. So there's a system called the Anomaly Report System, AR. And so, and basically that's where you put any kind of thing that is phenomenal. So you expect that number to be really high. And anything you read says for space station, anomalies happen every day. Some days more than one, some days 1 or 2, right? But they're happening all the time. But an anomaly can be anything from your computer shutting down unexpectedly to, a light not turning on. It can be little things, it can be bigger things, okay? But if you look at these numbers, right, like from 2000 to 2024, you see these two numbers because our first time we went up to 2019, the first time we counted, we came up with this 10,000. And then recently we just went back and added, and the only important thing to note here is, here we are 24 years into the space station. We know the vehicle, we know how it all works, and you still have a pretty high rate of stuff that happens. So it's not like it's, right? And so here you just see it distributed over time. And maybe you're starting to see something that's kind of typical of engineered systems, which is the bathtub effect, right? That it's a lot more at the beginning because you don't know things and it's the first time in the vehicle you're experiencing all the problems at the beginning. This is why you never buy a car in the first year or 2 that they're made, right? You wait, right, 2-3 years to get a new model. And then it gets a little better, and then it starts getting worse again once the thing starts getting old enough that things start breaking again, right? Which may be where we are here. So an average of about 150 anomalies, again, very, not critical necessarily, per mission increment, which is about it's about 6 months. A mission increment is 6 months. Okay, so just to give you a sense, like stuff is happening all the time, big, little. And even with little ones, how do you know it's a little one? Well, the ground tells you, right? So here's another breakout. And this is from another set of databases. So that was the AR, the Anomaly Resolution Database, right? 2 other ones are the FITs and the ARTs, right? So the FIT is the Flight Investigation Team. The Anomaly Resolution Team is the ART. This really only gets convened when it's a bigger deal, right? So how many? So here you're looking at, again, 24 years. And so we're getting to smaller, more reasonable numbers. But you see here, 149 anomalies over those years that required really, deemed critical. And, basically the MER, which is the Mission Evaluation Room, the team of the really core experts, manager will establish an anomaly resolution team, and they'll start really working that thing. Right? There's another little nugget in this. These are systems, structures, and mechs. This is power systems, guidance, navigation, and control. ECLSS is environmental control and life support systems. Look at that number, right? Like that is, okay. And there's two things about that. It's a bit of a chicken and egg, right? So first of all, people say, well, like maybe a mission to Mars isn't going to be that hard because we've already done a bunch of missions to Mars. We've sent rovers, right? And they've been okay, right? And they go and they, we land them, we drive the rovers around, right? And so now we're going to send humans. The sending humans and trying to keep the humans alive, which is a lot of this stuff. And these systems are the messy systems, right? This is the problem too, right? This is where you got water and you got clean water and you got dirty water and you got breathing, which is causing moisture, on those rovers to Mars, that system is pretty much off. It is the equivalent of if I want to launch a bowling ball from my yard into the neighbor's yard versus if I want to launch, a fish bowl and have those fish land nicely, not be disturbed, have their little air pumps and everything, right? And so the environmental control and life support systems turn out, they're the most difficult part because they're messy things and difficult, it's liquids, it's pumps, it's all interacting with electronics. And when something goes wrong with one of them, they're the ones that require the most urgency because they're the things that are like the shortest time to effect, right? They're the ones that'll kill the crew first, right? So if something happens to another system, you're not as worried as if you have a problem with all of a sudden your temperature's starting to drop or you're losing pressure, right? So this all kind of led us to focus in part on, things where the ground is dealing with emergencies in or urgent, events in those systems. Okay, so again, kind of just going through this, about 10,000 anomaly reports, about 450 of them were determined as items for investigation, which is also saying this is a big thing, we've got to go investigate it. Of those, 64, this is over, again, the 24, this is only the 19 years, right? So 64 were high priority, which means requires immediate attention because of possible loss of crew or loss of vehicle. Another 10 of them are what Johnson produces something, it's a foldable, it's almost like a map, and they call it the Z card. So and those are like another set of really important ones. And then we went and looked at those really carefully and said, how many of those have really required urgent response? And were it not for the urgent response, there actually would have been a bad outcome. Like your thermal system actually shut down, right? And you almost froze the ammonia that circulates on the outside. And if you do that, you breach the ammonia to water interface, and you have ammonia in the cabin, and the crew die, right? Like, and that, that's one of the number of very bad things that can happen. So that tells you, and this is we did not include extravehicular activities. We didn't include, like in Apollo, the landing on the moon. So this is a very conservative estimate that about, twice a year, you're going to have an event of high consequence that needs to be addressed right away. And if you can't, it has, possible mission ending consequences. Yeah. And we have to go and, solve that and make it available, make it possible for the crew to address those. Otherwise, the 9 months to Mars, we're not going to make it. Okay. These events tend to be urgent. They tend to be unanticipated, not anticipated in a surprise sort of way, like, oh, like I didn't expect this today. No, unanticipated in the engineering design processes, like things you didn't even think about, right? And so you don't have a procedure for it. You're like, what's going on, right? And of unknown source, right? Unknown origin. What could be doing this, right? We went and characterized like these really hard ones, and this is and that's what makes them hard. And again, what I want you to think about is, what do we do about this, right? Because these are hard problems. Like we're throwing some of our smartest people at this, right, on the ground to try and basically, and we have been successful, but we're throwing like 30, 40, 50, 60 people. We'll bring 80 people in, right, when these emergencies happen. How do you get that down to 4 astronauts, who need to resolve that? One last piece of, actually, one more. On the space station, there are actually alarms that sound, which drive the astronauts crazy. A Class 1 alarm is a fire, a rapid depressurization, or something toxic in the cabin. There's no troubleshooting that. The crew go and safe themselves in all those cases. They'll go and on the way to Mars, the idea is that there will be a safe haven. A Class 2 alarm indicates that crew or ground need to take immediate action to avoid injury or death of crew or damage ISS. Okay, so bad outcome. There've been a total of 666 of those, 660, up to that, on average of about 2.5 months. So if you distribute it evenly, which they're not, there'd be about every 12 days you'd have an alarm telling you you're going to die, right? And now mostly the crew don't even have to deal with this because the ground says, "Yep, don't worry, we got it," right? This is the other big part. And so even though a lot of these turn out, that the ground like knows and whatever, that is going to be something, again, that you're going to have to move on board, right? And then one more thing that I find interesting, I'm trying to give drama to the problem, right? But it is a big problem. This is from a study that was done in 2013 by Kathy Abbott at the FAA and Amy Pritchett at Georgia Tech. And it was really interesting. They were looking at commercial aviation incidents, accidents, okay? And they found that failure modes were unanticipated by designers. So in other words, the thing that went wrong was not like it's something that, the person, in 40%, more than 40% of major incidents, right? And then 10 years later, this is the NASA Engineering and Safety Center, our senior technical fellow for software, so this is Lorraine Prokop, just produced 40% of software errors. She looked back over the 60 years of software errors that caused big incidents. We're due to the absence of code, which includes missing requirements, capabilities, inabilities. So in other words, we didn't, failure to anticipate situations, right? And so we started then going and talking to like more people, and that is a pretty stable number. It turns out that when we build things and we say, okay, what can go wrong? And we do hazards analyses, and we do failure modes effects analyses, and we write, fault detection, isolation, and response, and we write procedures. We're getting about 60% of it, which is like really, amazing, right? And so and that's really the gap that we want to close, right? Because if we've anticipated it, then the crew will have a procedure, or there will be a fault detection system that will detect it and stop it. The problem is that 40%. And those are the ones that those counts before are capturing. So actually, before I get here, let me pause there for a second. Any thoughts on, so if you had this problem, because I have to say that I worked on characterizing this problem for about 4 years, and about a year ago, just over a year ago, all of a sudden we got funding. I'm now part of the Mars Campaign Office and something called the Earth Independent Operations Domain. And we don't have a lot of money, we have a little money, but we have now a team across the centers working this. But I remember that there was a moment where there was like what can be done? What can you do? I mean, that's a hard problem, right? Because in a way, we're still at this point where computers really can't deal with things that they haven't seen before. And that's an ongoing reality that, I'll talk about more, right? So what ideas, any thoughts on like how we begin approaching this, closing it?
They are.
Yeah.
I think you have to admit Murphy's Law is a real phenomenon.
Right.
And the estimate of failure, usually systems, not sometimes very exotic, everyone pretty familiar with, but yet something unusual.
Yeah.
Hello?
I see it, but it's, for example, the RAND Corporation kept paper, it was a study on software. And thinking about it, remember, solutions are one of the leading causes of problems.
Right.
So you fix the software and you actually introduce errors. So that asymptotically, it's always about couple lines of code per 100 of an error. Never goes away.
Right.
It's always there.
Yeah. And that's a pattern that we see too, right? We see that you think that it'd be dropping off significantly, it doesn't, and it's a kind of endemic to engineered systems, right? And so you're right. And by the way, one thing that you said that we've heard too is at one point we were talking to sailors on aircraft carriers, and one of them, they said, look, the ship, et cetera, and they're like, that box, like, can we get into that box? You can't get into that box, and they're like some box that you might need to repair, right? Nope, like you can't get into that. Nothing will ever go wrong with that box. And then what they said is, inevitably something will fail with every box that's closed as if you'll never have to, right? So everything that you build as if it's infinitely reliable, right? We'll have because, we're not we're very good engineers. We're not perfect engineers. And therefore, if you put something in a hard environment for a long time, almost everything will have a problem and things you didn't anticipate.
Their space is bigger than our space.
Right.
So you just resolve yourself to I'm surprised that they happen to have more failure space shuttle.
Yeah. And again, it's because we can it's almost like we got the mechanics we do have the mechanics 24 hours a day on the ground, right? It's like,
I had some experience with satellites commercial. And they're sure it's pretty complicated, but various phases, life insurance and all that. But the assumption was that about 5%, a single-digit percentage would fail on launch for some reason.
yeah.
So when the shuttle came up, they had a lot of people look at it. They said, no, it's about 1 in 10,000. So it's pretty marvelous, right? So what actually happened? Well, they had, I think, about 130 shuttle launches, and they do those out.
Yeah.
That's typical launch statistics for
Yeah.
satellites.
Yeah.
So it's nothing changed.
Exactly.
Right.
Yeah. You have that data too. So of not here, but we looked at that space, launch, and it just, we're not getting rid of the problems. We have another.
Yeah, it just sounds like nothing changed except risk.
Right.
So,
Yeah.
For the shuttle, the engineers are forced to be optimistic at some point. And it's bad.
Yeah. Oh, yeah. People are. Yeah.
It sounds like for the trip to Mars, then spacecraft can host tanks.
Like the Nina, the Pinta, and the Santa Maria. Yeah.
Large spacecraft.
That's right. And so there are, and again, part of our problem, of course, is how cost limited all this is, right? And how incredibly expensive all of it is. But certainly having 3 vehicles in tandem would make a difference. But by the way, one of the biggest challenges, and this is true of submarines too, right? When we talk to submarine, why do submarines that go down for months have to come back up? It's because they run out of food. So again, it's that. So the more humans we send, the harder that problem gets too, right? So here, let me just so I can kind of pull it together. Sometimes we're gonna from the really hardcore NASA engineers, we're gonna make this thing so reliable nothing will ever break, right? What we were just talking about. And so anomalies don't occur, literally, we're working on high reliability systems, like Toyota, right? And you're right. And these are, again, these are one-off systems that we're putting them into hard environments. And even, none of us even like taking our cars to the mechanic because they're not going to figure out what's wrong with a car that has been, that there are a million of them, right? Artificial intelligence will address all anomalies. I'm going to talk a little bit more about this one because I think, obviously this is where some of the promise lies, but there's also, being aware of those limits is interesting. Mission control on Earth can continue to address anomalies even with delayed communication. We get this one from the mission controllers. Don't worry about it, we got it. And then training can be amplified to prepare crew to address all anomalies. In other words, we're going to train the crew to, and this one often comes from, mission ops people, although you ask crew and the crew are like, you cannot put any more in our heads. You cannot put, each crew member typically already has 2 areas of expertise. They're already a pilot and a mechanical engineer, or a doctor and a pilot, right? And so all of these have to come together. None of these will work by itself. And then some of the other ones that we hear sometimes is we already know how to do a Mars mission safely. No, it's a totally different thing to send a box that's off to Mars as opposed to humans. Mars rovers have a lot of autonomy. It turns out they have very little autonomy. We're commanding them very regularly. ISS crew has a lot of autonomy, and that is, people will often bring that up. Like they'll say, Alonso, like the ISS crew, they want more autonomy. I'm like, yes, because they're not flying the vehicle. It's being done from the ground. It's a laboratory in space, so they're up there doing science, and they're running their experiments, right? So yeah, of course they want autonomy, unless things happen, and then they don't want autonomy, right? And so let me just wrap up here with a bit on how we're approaching the problem. So we've got like a few kind of basic assumptions here. One is the crew will be useful as highly adaptive, flexible problem solvers. So it turns out that, and I can say more about this, and I can talk more, as well if there are questions. But each one of us with our little human brains is still much more powerful than any given computer, but also in very different ways. So AI has become better than humans at certain things already, but humans remain far better than AI at certain things. And the interesting thing is that AI right now, I think, most of us who are in the field feel like it's progressing in an orthogonal direction to human intelligence. What we're seeing in AI is not what we used to envision back in the 60s, the 70s, the 80s, which is like we were trying to produce intelligence like human intelligence. This is what we're seeing in AI today is fundamentally different than human intelligence, and it's developing in a different direction. So humans remain a different kind, and we're particularly good at adaptive, flexible problem solving. We're particularly good, like most animals, at things we haven't seen before, right? So why is that happening, right? Okay, second is ground control will manage everything that it can, everything that's not urgent, so assume that. Onboard systems will automate as much as possible to reduce crew load. And then the two big things, and this is what I'm really gonna just spend this last bit of time talking about, is in the last 12 years, two big kind of things have happened. Everything that is AI today is these two things, right? For decades, we worked on AI, and it was all rule-based systems, if, then, and you're trying to write out all the rules, and that's what I did. My whole postdoc was in making little rules for human systems integration AI. And what changed is in 2012. In 2012, right, there was a publication by a paper by Jeffrey Hinton on convolutional neural networks. I don't know why it's doing that. It's probably that. Physical failure. Sorry. Yeah, that's right. So in 2012, right, there was a paper that was the first real demonstration that if you did a set of transforms on large data sets, it wasn't clear why, but you could slowly start pulling out patterns, okay? And that turned out to be an approach, and that's, the T in GPT is transform, right? And it's just where we are today, right? And again, like, if you actually dig into how it works, it is weird, it's like magic, but nowhere are you inserting really any intelligence. You're just transforming a set of vectors in another vector table, until all of a sudden you're pulling out patterns from the data. And really, what AI today is very large-scale covariation detection, right? And that scales up. That really is what gives us face recognition. It gives us the language. It gives us. Okay. The other thing that's really changed, and some of that large data is coming off the web, right? Language, as we digitize books, images, and all of a sudden so much data became available. But sensors have changed dramatically in the last decade too, and deep sensor networks, and there's sensors everywhere, right? So 2 days ago, so our son and his girlfriend just bought a house together in Boulder. And so as a little present, we gave them a washer and dryer. So my son called me and he goes, Dad, the washer and dryer says it has AI. I'm not kidding, right? I was like, Right? You know, they say that's crazy, right? Or silly, right? And then he called me the next day and he said, no, you're not going to believe this. So, you know, plug it in, run our first load, and it popped up and it said that the exhaust vent on the dryer was 80% blocked. And so he said they went in, and sure enough, I mean, they didn't estimate 80%, but it took them 2.5 hours to get this thing cleaned out all the way through. And then it was down to 0%. It was happy, right? And so I thought, okay, well, that's a lot of that is sensors. And then some of the 80%, I don't know where the AI is, but that's the fact that we're putting sensors in everything, right? Everything, like sensors have become cheap, sensors have become like easy. I remember a big transformation when the thermostat, at some point our thermostat in the house was having an issue, and I put one of those Nest thermostats, and I was like, what's wrong with this thing? And so, you know, I Googled it, and sure enough, you can, you know, dig in there and it'll tell you, you know, how many volts, how many amps, whatever it's getting on each one of its little wires, right? The old honeybee thing, or not honeybee, the Honeywell thing didn't do it, right? All of a sudden you're being able to get data off things, right? And that is a giant freebie. And so this is what's happened in the last decade. This is everything we're seeing. The self-driving cars, the works, right? So, okay. So what we did is we started taking big anomalies that had happened on the space station. So this is a 2013 thermal cooling system. I forget what that EA is. And so loop A pump, so 2 loops on the space station, one of them shut down. They're not fully redundant, so it started getting hot in there, or at least that was the worry. And so you see, this is what the crew does. This is what the onboard system events are, all these alarms. Here are commands, here's what mission control is doing, and here's what the mission evaluation room is doing. Okay? All this stuff that's being, the ground really kind of doing all this stuff. And we looked at it and we said, of this, how much, you know, what is it that needs to be moved on board? And let me enlarge this one just to make it a little more. So, first of all, you had a large number of caution and warning and advisory all at once, right? You just have all these alarms. And they have like, you know, and the crew was like, wait, what's going on? And the ground was like, oh, don't worry about it. Okay, because, you know, at least not, this one was one where they did need the crew's help. Somebody needed to be tracking trending data. Was it getting better or worse? Of course, you have all these people on the ground doing exactly that. They're sitting in the main room of mission control, which is what you see, and they're looking at the telemetry on the screen. Also, if you're on your way to Mars and you have even a few minutes of con delay, the ground won't command in the blind. The ground won't command something without knowing, being able to know, because you can do something bad by accident if you don't know the effect right away. You have to need awareness of small deviations in data. They needed to know. So one of the things that happened in that one that made it so dangerous is that the cooling loop shut down. They're like, cooling loop shut down. So they start right away a procedure to start it up. And they started it back up, but they started it up in what is called bypass mode. So there's a valve, they close that valve so that nothing is streaming by the ammonia loop. So you don't risk freezing that thing. Well, 2 weeks later, they finally figured out on the ground that what was happening was that valve, they commanded it closed, it reported closed, but it was a quarter open. So they were still running water interfacing with the ammonia loop, and that's like they almost breached. And but they didn't know any of that at the time, right? So this is all they're trying to figure it out. They're not understanding why the alarms are still going, why the cooling loop keeps shutting down, right? And eventually you get it to where you're working it in a more timely way, which now the ground would, hopefully still be able to take. But early on, what's happening is that all of this activity, all of it has to move on board. So we took all this and we said,
oh, come on.
These are the Mars pain point analysis. You don't have to read this, but this is like alarm triage. 50 alarms go off at once. Commanding, right? So the ground's not going to help you command because if they don't know the outcome, they're not going to command from the ground. Next, worst failure analysis. The ground's doing that right away. Procedure execution, knowledge configuration, etc. This is all the stuff. So we kind of pulled together everything that is a critical function that the ground is doing in real time, kind of abstracted away from the problems. And we did a whole bunch of these analyses of how we do mission operations now, just to understand what functions need to be put on board one way or another. We took those case studies that I just showed you, then developed use cases, and then those got turned into like a functional decomposition, which then is shaping our analysis of or shaping basically how we're investing our budget in the technology. And I'll tell you a little bit about that, right? So basically, what we then decided is, we said, look, there are a bunch of elements here. So one is situation awareness. How do we know when there's a problem? And, when there is a problem, you have to notice it in a timely way. You also hopefully have some sense of what was happening before. The way we do that is we have in the order of 20 people sitting in the mission control room right up front, right? Like looking at telemetry 24 hours a day, right? That's how we do it. That's situation awareness. That's how we do it. Are we going to have crew members on the way to Mars looking at telemetry? Every time I ask that within NASA, people are like, well, no. I'm like, okay, well, we better have a solution to that problem. Troubleshooting safety critical unanticipated anomalies, and, which again, I've talked about a lot. And then executing any complex procedure where right now the ground is providing you oversight. And then a focus on the environmental control life support systems and also the electrical power systems. It turns out the electrical power systems aren't that interesting on their own. Like if there's a failure, boop, there's a failure. But the electrical power systems, it's a bit like the circulatory system in a human, right? So when you go and they draw blood to see how your endocrine system is doing or how your immune system is doing, right? Your blood carries all sorts of information about how your kidneys are doing, and right? Power systems are just like that, right? Power systems carry all sorts of information about the state of other things that are plugged into it, right? So if a fan suddenly starts getting a little, cranky and it'll draw more. You'll see a change in the pattern, right? So what we said is, look, okay, AI by itself remains poor at dealing with situations and conditions that it hasn't seen before, okay? It's, ChatGPT can generate things, but only based on stuff that it's read, so if it's a whole new thing that you haven't seen before, ChatGPT is not going to come up with it. At first, my first thought was, when ChatGPT came out, was like, okay, ChatGPT will be useful for the crew to write their resumes for their next job once they come back to Earth. As we spend more time, I think that there is relevance. But here's the thing. This is maybe like the nugget. Because otherwise this would be impossible. If we think that all anomalies are unknown unknowns, there's not that much, it's just a hard problem, right? What's interesting is, so unknown unknowns, like we're something like you just really like a lightning bolt from Venus, right? We never even knew that could happen, right? And those are exquisitely rare. Almost no incidents in, you look again across engineering systems, et cetera, they're not unknown unknowns, they're unknown knowns. It's in your data, you can't see the pattern. And that is the power, in a sense, of that AI is giving us, and you take that in combination with the kind of the plasticity and flexibility of human reasoning. So then the question became, can different AI modeling approaches work, with crew to close that onboard expertise gap? And so we've got two areas of focus. One is to take the large data analytics, right? So exactly what we think of when we think of ChatGPT and all the machine learning, et cetera. We only have one flavor of large data here, which is telemetry. So the stream of data that's coming from the systems down to Earth, now you're going to be analyzing that. And right now we don't do any kind of data analytics on telemetry, right? You got humans watching it. So you bring that and then take your well-established AI rule-based, logic-based models and you map them, right? And this is what we've been doing. And this is what's basically, let's just at a meeting, there was a DOD meeting and this is, I think, it's the next thing that's happening, is beginning to take a classic, AI, tool like Teams, which is a rule-based system. And then you're looking for, clustering, and you're using Kalman filters, and then you're using neural networks. You begin to stack these approaches, different kinds of AI working together, okay? So you're doing the large data analytics. You're also doing large data analytics all the way through, so that once you've established, for example, if you're monitoring the power systems, this is how all the systems behave. And then at some point, one starts behaving differently. Again, you can say, hey, this thing's doing something weird. And that gives you some anticipatory data. But the other thing is maybe there's some odd signals here and there, but there's not a clear pattern enough to tell you that there's a problem. So the system might not tell you there's a problem. But let's say that one day something bad happens. You can go back and go, okay, oh, yeah, those things were maybe precursors, or at least bring that as evidence forward. We do none of that now, right? So the thing is to converge on the unknown knowns. Now, the other way that data is hard is for I talked at the beginning about anomaly reports, right? And Ken and I both, work at NASA. We work in the same division, and right, we've worked on problem reporting systems for a long time, right? And problem reporting systems, it's, there was a problem, then it gets written up, and it's in English, right? And it's an engineer of that kind of system writing it for another engineer of that kind of system who checks it over, and then eventually, like for example, the shuttle couldn't fly with an open problem. You had to have every problem had to have been closed or waived, right? And so getting something useful out of that data requires expertise. And so again, we throw experts at it on the ground. That, for example, is somewhere where ChatGPT can help, right? And we're working on that too, right? Kind of tuning these things to go in and pull out of that data, like, has something like this happened before, right? It turns out it's reasonably good at things like that. Not perfect, but maybe better than zero, right? And better than having somebody go read 1 million problem reports, which is what there were for Space Shuttle, right? And that's hard. And by the way, one time I was on a team, it was like the second to last Space Shuttle mission, and they started putting in the problem result, there was something called the SPIT, the Shuttle Problem Investigation Team, right? So I sat there, part of the overnight team for that whole mission. It was midnight to 8 in the morning. It was when all the data collection was done. And they put a really experienced person who'd like worked the mission for years in each one of those meetings. And that person, I would basically a problem would happen. I say, go look at problem report number 9,224. Whoa, right? But again, we're not going to. I mean, maybe you want to be sent into space, but that. So again, trying to. I was talking. We were in a meeting about this today, and one of the guys that we're working really closely with said, I don't think we're going to crack this, because if we crack this is like Nobel Prize stuff. I'm like, nope. We're not pretending that AI is going to close this gap of getting us to unknown, to basically solve problems it hasn't before. We're basically using all the tools around us to try and close our lack of understanding of the unknown knowns, and then putting that in front of the crew. And I'll say, one other area that's a challenge that we're really focusing on. So again, earlier this year, I was at a meeting, and there was a team there from the Navy, and they were working with an autonomous ship that they have down in San Diego called the Sea Hunter. And this ship, no crew, just goes around. And so, I don't know, 2015 or so, I was down there, and we went on board that ship, and actually we went on the ship physically, because there's no on board. You can't go in. There's no, right? It's not made for humans. And so it just had its first mission, for one thing. They really had a hard time getting this thing to behave in a way that they weren't nervous that it was going to hit another ship or anything like that. And one of the senior researchers reported that they had a big advance, that it used to take 6 months for something that, say, a sailor had seen on a ship. Let's say there's a shoal that for some reason, low tide, it shows up, right? And then to have that go into the AI system of the Sea Hunter, 6 months, right? Of a human sees that thing and goes, it's a this, and then for it to be programmed over here. And they said, we've got it down to 4 days. Okay, and they were super happy with that. And at first I was like, oh, 4 days. And you realize, no. It has to be real time, right? And so that whole team of people, it was a human machine teaming workshop with DARPA, Navy, Air Force, and a bunch of companies. And everybody realized, right now we're doing almost no real-time interaction between real AI. I mean, we can ask Alexa something, but it's a one-way conversation, right? If you ask Alexa, what's the weather tomorrow in Miami? I'll say, 98 degrees. Okay. What are good restaurants? They'll say, where? Right? There's now that's going to improve, but still, that kind of real, quickly getting an actual observation that could be human as a sensor, human detecting, there's a burn mark here, or human as a hypothesis generator. I wonder if it could be this, right? Because I saw this other thing the other day. How do you get that into the AI quickly in its own representational mode, right? And in which part of it, so that it can be used in an iterative way, right? So that's another big challenge. So those are the things that we're taking on to just try and begin closing that gap. And let me just say that just a lot of people have been involved in this. So I want to just put it's been a really good team. So that is it. Thank you.
So if you have questions, I have one already online. And I'll be excited again if you guys have questions, of course, let's as well. So we had a.
One more.
So you made it, so Dr. Vera, you made a good case for the time operations. This gentleman, Nick, is curious about whether you looked at the impact of asynchronous communications with family and friends. Time delays. So
Yeah.
it's a major source of support, emotional support.
Yeah. Yeah, so there's been really a lot of research. I think a lot of the research that happens in these habitats where you isolate people is very much on that, right? It's on the kind of social, emotional state, the effect on the team, the effect on the individual. And so, like I said, I mean, there's actually been a lot more research on that than there are about how do I keep the vehicle alive, right? But yeah, and those are issues, and I think there's a lot of effort there too, to how do you begin to close that gap? Obviously, we used to do it before by writing letters and telegrams, but it's obviously it's different too when you're in that kind of a difficult, isolated environment, right?
Questions from the audience?
Yeah.
Thank you so much for this wonderful presentation of this strong perspectives. This reminds me the concept of predictive instrument failure existing in instruments that can be the default devices and packaging. So one question. You also mentioned, I think, that association between missing software functionality because you didn't have the requirements.
Yeah.
So I was wondering, is there any concept in this system, in this planning, of providing toolkits in a sense to the people involved so that they can actually create that software component, whatever flow or whatever you want.
Yeah.
Because that doesn't, I don't think that they're compatible with themselves.
Yeah. I mean, it's a good question, right? And I think you're getting at that question of the 40% of stuff that, that we don't have and are there better ways to, I mean, here we're assuming that 40% is stable, and how do you deal with it when it happens, right? And to your point, like, if you're building into any system ways of either anticipating an error or dealing with it, that's your 60%, right? The 40% is, so partly it's you're writing code about a system that's going to go into an environment that, and so.
So one example would be, here you're also the root cause analysis concept representing this system essentially analyzes the data from those systems to these hints, these problems.
Yeah.
That could be maybe your workplace someday, a little change, one little change somewhere, it's likely complicated.
Right.
Sort of concept of.
Yeah. And the hard thing is that, again, so we have all these engineering approaches to modeling systems and doing, model-based systems engineering, which has its own high costs, et cetera. And all our tools, but again, it only has in it what we thought to put in it, right? I mean, there's this great expression, which is that, I don't know who said it, right? But the problem with simulation is that it's doomed to succeed, right? And because, right, we write it and then you test it and then, hey, it worked, right? And so, we actually had, there was a team at UC Davis recently, like working on building some simulation, but for physical ECLIS systems, environmental life control systems integrated, and then a digital version of it. And they said it was much harder to get the real one working like it was supposed to than to get the digital one, right? And this is the problem, right? The physical world is really, we still don't deeply understand it either, right? Yeah.
Just one minor point of it. Now, a lot of this, like you said, it's predicated on the need to send humans.
Yeah.
If you don't send humans, it's a lot simpler.
Yeah.
And the argument is that even the Apollo program, there's no major scientific discovery.
Yeah.
It was like big attention.
Yeah.
And there was only one person who was a scientist of the whole team. And they learned, and what they learned is the moon is roughly made of the same stuff as the Earth.
Exactly.
So,
Yeah.
I'm wondering
And by the way, we talked to Jack Schmidt is one of the four. So he was the scientist on.
who's a senator later.
Yeah, he was the one scientist. He was the geologist, right?
One geologist. So
Yeah.
this was a big adventure, as you understand. The question is,
Yeah.
really, if you thought about it long enough, you would justify any moral obligation.
Yeah.
And you're going to kill some people who keep doing this. That's what
Yeah.
that's the
I mean,
problem.
that's it's always there's a bit of an existential question there. There's some practical questions too. I mean, some of this has to do with the political climate, right? So some of it was the space race, and we may be in it again, by the way, which is driving a lot. So it's like, and it's explicit now, right? I mean, like for the first time in my 25 years at NASA, our NASA administrator said we have to beat the Chinese there, right? You don't hear that kind of rhetoric generally. You really don't. To beat the Chinese there. Okay, so there's that. There are commercial possible things, and the moon has a bunch of things, which also is bad, right? We're going to go drill holes on the moon now, right? Again, I'm passing judgment on what's good and bad there, but okay, so that's another thing, right? And then there's a more fundamental, question too, which is, we're either trying to get off this rock or we're not, right? In the long term, right? So, exploration is something we've always done, and like really, if we stop trying to go to the next thing to do, that's I think to a lot of people that feels like, that's the, and now there's still a lot of things to explore on Earth, but that notion that going out and finding out more is kind of part of our fundamental trying to understand science. I think is fundamental too, right? So you're right. The moon was a rock that's very close to us. Mars, may have a lot more, but again, and Europa, right? Now, at this point, we're not thinking of sending crew to Europa, right? It's to Europa, it's a lander that would drill through the ice, right? I think basically all indications is that Europa is a frozen, it's a water planet, right? An ocean world. So it's and then there are a few other things too, right? So I could go on. I mean, obviously I've spent a lot of time on. So most people think that as we build, a mission that, we're basically filling up a rocket with $1 billion and sending it to Mars, right? No, the bulk of that money and investment stays as technology on Earth and expertise, and then there's the whole. I mean, the impact that NASA had in terms of especially Apollo era, on inspiring a whole generation of engineers, right? So those things all get weighed, I think, in that scale. I don't know. I don't think there's a right answer, but I don't think it's also obvious that that it's a thing we shouldn't necessarily do.
Yeah, I'm wondering if there's any program afoot that would put up in orbit around the Earth convenient, easy to repair, obvious. But something that's not an ISS, which has built-in Earth support built into the whole mission.
Yeah.
But something where we are specifically, the US or the Earth, we're specifically trying to get it independent of Earth interaction.
Yeah.
You have the convenience of quick repair and turnaround, and you're not killing people quite
Yeah.
so easily.
But we can test it out.
And you can test it out, and after 5 years of running without a fault or
Yeah.
and maybe some.
And that is very much the idea for Gateway. So Gateway is, yeah, that's exactly the intent, is you put Gateway around the moon, hopefully make it possible to be more Earth independent, right? So, by the way, space station in its initial plan was, it wasn't going to be flown from the ground. It wasn't going to be trouble, right? The crew were going to be doing that, and eventually, not only, did that not be the case, right? You needed a lot more people than was expected to do it from the ground. But Gateway is partly that, and then the idea too is exactly as you described, that the vehicle that'll go to Mars will be parked at the Gateway for 5 years, 10 years before we go, right? And maybe more than one, et cetera. Yeah, to begin to explore that. And, the lunar missions are gonna like shake out a lot more too if they go, if it all works, right? So, you had a question too? Yeah.
My sense from this talk is that a crewed mission to Mars would be incredibly difficult. It's impossible.
I painted the picture for one of the challenges. There are a lot, right? There was, so almost regardless of, for example, just to give you another example, regardless of how much conditioning, like the crew do on the way, so in zero gravity, they're going to lose a huge amount of like just muscle strength, right? Now, when they land back here on Earth, they basically get out of that vehicle and people take them and, carry them, and it takes a week to 2 weeks to really be walking normally again. Here, you're going to land on Mars, you have to get out of a vehicle, right? And so what's the plan for that, right? And there was my wife and I were actually, this is a year ago or so, we're walking up in the hills here, and it was an early morning call, so we walk early, and I said, okay, I'm going to take this one. So I was on my phone, I had it on speakerphone, and she was listening. She's a finance person, right? But I think she pictures NASA being much more advanced than it is, or really our space exploration, right? And so somebody was proposing how to recondition astronauts once you're in the vicinity of Mars, right? So you get to Mars, before you go land on the planet, how do you get your muscle strength back? And the proposal was that we're going to put a tether on the outside of the vehicle, put a chair out there, put a crew member, and spin them around for 8 hours, a day for 2 weeks, right? And she was listening to this going like, what? Like, I was like, yeah, I mean, it's hard. It is a hard, and we can't build big vehicles, right? I mean, Wernher von Braun, when, Wernher von Braun was like, he actually had some of the early architectures for a Mars trip, but they envisioned a much larger vehicle. It turns out that Earth's gravity well is so, it just makes it very expensive to get anything into space, right?
I was curious about what happened to the old concept of the rotating space station.
Yeah. So it's prohibitively expensive, right? To build something that big. I mean, in a space station that we built over 20 years, a little at a time, sending module. I mean, maybe we could, but it's, and then to get that moving, right, at 17,000 miles an hour. Yeah. It's not impossible. Again, and some of this, for example, my whole problem would go away. This whole thing that I told you, if somebody said we're going to send 80 crew, right? Be like, okay, good, right? And it's still risky, but you've improved it, right? The problem is trying to make it say 4 or 6, right?
We have another one online. Let me see if I can unmute. John T. If you can hear us, John T.
Yeah, hi. Can you hear me?
Yep.
Yeah, thanks. Actually, the first time I've heard about Gateway, because it was raising, you guys were already starting to talk about the same issues that I was thinking about when you were doing your presentation. there's been very little data on the survivability of humans outside of low Earth orbit for, more than a few days. And the reality is the data we already have suggests that there's significant human health problems just 15 months out in low Earth orbit. And if you consider 2 years out with cosmic radiation, we're going to have to create a much bigger ship just to protect humans, let alone, trying to condition them to get to Mars and back. Seemed to me like the Gateway project would have to, include, and it would be really great to hear a little bit about the Gateway project in another meeting. But, I would think that you'd have to create some sort of system and have people try to survive in such a system 2 years out around lunar orbit or something like that, and then send something to the moon, Mars and back before you would dare to let humans go there. That would be in itself probably a 10 to 20 year project after we have a lunar base.
Yeah, absolutely. I think everything you said is right. And so the NASA Engineering Safety Service Center at some point did in 21, so not at some point in 2021, a study on what are the 3 big risks for a human mission to Mars. And one of them in the end, and this for me personally was a big deal, was this. And then so they decided, we don't know how to do Earth independent missions. The other 2 have been known for a long time. One of them is microgravity. It's very, very bad for humans. And then the other one, which is even worse, and it turns out that after years of investment, we don't really have much of a solution for, is radiation. And so for example, you can hold the water that you're going to have, and you're going to use a closed loop system. So you're recovering all your water, which we do a lot of on space station now, but like to 90%, not 100%, right? But you have all your water on the outside of your vehicle, for example. So and so that provides a certain amount of radiation blocking. But you're right. It's one of the other very big challenges. And you said a couple of other things that are important, right? We've had the longest an astronaut has been in space has been, in the order of 1.5 years. We've had like a handful that have been there more than a year, right? So very few, so very little data. But on top of it, it's all on the space station, which is within the Van Allen belts and still pretty protected from radiation. So we have not solved the radiation problem either. So that's another biggie. Yeah, so there are many, many problems. My only one is this one.
I'm thinking in terms of time, we're close to shortly. I just have one additional question, suggestion. Do you have anyone whose sole goal is just act like a bad monkey wrench and just purposely, randomly break things and see if it's survivable in some random, whether it's a person or a computer or something?
Yeah, arguably most of the mechanics at Kennedy Space Center, but no, I mean, no, I don't think we have that. Although, I mean, it is built into the engineering process, right? The try to break it, right? Like, especially for this kind of stuff, right? So we're, again, trying to build systems that are reliable to 15 years right now. And a lot of the bit is putting it through, right? I think you've seen, right? So, there's a watch called the Omega Speedmaster. And when the Speedmaster, it was Mercury, it was 1965. NASA asked all these companies to provide watches, right? And they did all the bad monkey tests on them, right? And I think the Speedmaster was really the only one that actually survived. But that, if you talk to anybody in the space industry, that set of tests kind of thing, you apply it to everything, right? To be rad tolerant, shake tolerant, just everything, right? But another big challenge that we have is that almost no company on Earth cares about making radiation tolerant chips for computers, right? So there's very little radiation tolerant, actual hardware. And so for example, displays have electronics that are really radiation sensitive, right? So are we gonna have displays? Now Mars is far enough out that we'll probably have retinal implants or something, right? I don't know. But still, the idea that there are problems we have now that may go away, but still there are many. It pushes on, and to your point, right? In some ways we're going to ask ourselves why, and I think it's a good thing to ask ourselves. but it pushes on the development of so many, areas and technologies that again, all have value in the long run, along with, challenging a whole new set of engineers and people to do it, right? So,
So I want to say thank you.
thank you.